How about the expectation value of the Hamiltonian in a stationary state? You would imagine somehow this has to do with energy eigenstates and energy. So let's see what happens. The expectation value of the Hamiltonian on the stationary state. Well, that would be integral dx stationary state Hamiltonian stationary state. And we're going to see this statement that we made a few minutes ago become clear. Well, what do we get here? Dx psi star of x e to the I et over h bar h e to the minus I et over h bar psi of x. And h hat couldn't care less about the time dependence. That exponential is irrelevant to h hat. That exponential of time can be moved across and cancelled with this one. And therefore, you get that this is equal to dx psi star of x h hat psi of x, which is a nice thing to notice. The expectation value of h on the full stationary state is equal to the expectation value of h on the spatial part of the stationary state. That's neat. I think it should be noted. So it's equal to the h on little psi of x. But this one we can evaluate, because if we are in a stationary state, h hat on psi of x is e times psi of x. So we get an e integral dx psi star of psi, which we already showed that integral is equal to 1, so we get the energy. So, two interesting things. The expectation value of this quantity of h in the stationary state is the same as the expectation value of h in the spatial part, and it's anyway equal to the energy. By the way, these states are energy eigenstates, these psi of x's. So you would expect zero uncertainty because they are energy eigenstates. So there's zero uncertainty of the energy operator in an energy eigenstate. There's zero uncertainty even in the whole stationary state. If you had an h squared here, it would give you an e squared, and the expectation value of h is equal to e, so the expectation value of h squared minus the expectation value of h squared would be 0. Each one would be equal to e squared. Nothing would happen, no uncertainties whatsoever. So let me say it once more in general, being so important here as a comment, that the expectation value of any time-independent operator, so comments on the expectation value of any time-independent operator Q in a stationary state is time-independent. So how does that go? It's just the same thing. Q hat on a psi of x and t is general now. It's integral dx capital psi of x and t, q hat psi of x and t, equal integral dx. You have to start breaking the things now. Little psi star of x e to the I e t over h bar. And I'll put the whole thing here. Q hat psi of x e to the minus I e t over h. So it's the same thing. Q doesn't care about time. So this factor just moves across and cancels this factor. The time dependence completely disappears, and in this case, you just get this is equal to integral dx of psi star q psi, which is the expectation value of q on little psi of x, which is clearly time independent because the state has no time anymore and the operator has no time. So everybody lost their time and we're in good shape. The second comment is kind of a triviality, but it's important to emphasize. Superposition is always true, but the superposition of two stationary states is or is not a stationary state? No. No, good. It's not a stationary state in general because it's not factorized. If you have two stationary states with different energies, each one has its own exponential, and therefore the whole state is not factorized between space and time. It's one time dependence times one space dependence plus another time dependence and another space dependence. You cannot factor. So it's not just a plain a fact. So the superposition of two stationary states of different energy is not stationary. And it's more than just saying, okay, it's not stationary. What it means is that if you take the expectation value of a time independent operator, it may have time dependence because you're not anymore guaranteed by the stationary state that the expectation value has no time dependence. That's how eventually these things have time dependence, because these things are not evaluated on stationary states. On stationary states, these things will have no time dependence. So, and that's important because it would be very boring in quantum mechanics if expectation values of operators were always time independent. So what's happening? Whatever you measure never changes, nothing moves, nothing changes. And the way it's solved is because you do have those stationary states that will give you lots of solutions. But then we combine them, and as we combine them, we can get time dependence, and we can get the most general situation.